Hello students, today we will study some important topics from chapter Atoms. In this lecture we will cover NCERT section 12.1 and 12.2. This is the disclaimer. So let's start by focusing on different atomic models that scientists have developed over time. We will look at the Thomson, Rutherford and Bohr models. Each model tried to explain what atoms are made of and how their parts are arranged. Okay, so what is the strategy for competitive exams here? Okay, so you have to focus on understanding all the atomic models. Okay, and also you have to learn the Rutherford scattering experiment and nuclear discovery, because that is very important topic of this chapter. Okay, you have to learn the concept. Your concepts should be very clear regarding the Rutherford scattering experiment. Okay, so you have to master the Bohr's theory of hydrogen atom. Okay, Bohr's theory we will discuss in this chapter. Also you have to uh, you have clear understanding of spectral lines. You should have clear understanding of absorption and emission spectra, okay, of hydrogen atoms. And you have to practice the spectral series calculation, Lemon, Balmer, Paschen series, okay, and other series. Also you should study the atomic spectra and relationship between the energy levels and emitted photons. Okay, that is also very important topic from the point of view of comparative exams. Okay, so you have the relationship between the energy levels, the radius of the electron in any orbit, okay, and Bohr postulates, that are very important topics of this chapter. So for please visit https://forum.pruter.ai for book recommendations and guidance. Okay, so for further reading and guidance, please visit this website. So let's start by looking what you will be able to do after this lecture. Our focus is on atoms and we will be building your understanding step by step. Notice that we are going to connect historical models with experimental evidence, which is the key part of how physics develop. Okay, keep in mind that each point we discuss will help you see how current understanding of atoms came to be. Okay, so firstly, you will be able to understand the historical development of atomic models. We'll look at how scientists moved from Thomson's plum pudding model, which pictured the atom as a sphere of positive charge with electrons scattered inside. Okay, and how we came through Rutherford model to Bohr model. Okay, you will be able to analyze the alpha particle scattering experiment, which was crucial for establishing the nuclear model of this atom. Okay, so also we will recognize the limitation of alpha particle scattering experiment, okay, in explaining the atomic stability and spectral phenomena. So this is our index according to NCERT. So we will that the topics that we are going to cover today is NCERT section 12.1 introduction, and then NCERT section 12.2 alpha particle scattering and Rutherford nuclear model of atom. Okay, so let's start by looking at how by 19th century scientists had gathered enough evidence to support the atomic hypothesis of matter. This means that matter is made up of tiny indivisible particles called atoms. Focus on that this idea was not always accepted, but over time experiments and observation convinced scientists that atoms are the fundamental building blocks of everything around us. Okay, so in 1897, J.J. Thomson experiments on electric discharges in gases, okay, revealed that atoms contain negatively charged constituents that are called electrons. Okay, so Thomson found that atoms contain negatively charged particles called electrons. These electrons are the same in all types of atoms, which was a big step in understanding atomic structure. Okay, highlight that this was the first time scientists realized atoms were not indivisible but actually contained smaller parts. Okay, so notice how even though atoms have these negatively charged electrons, atoms themselves are electrically neutral overall. This means the total negative charge from the electron must be balanced by something positive inside the atom. This observation led scientists to question what else must be present in the atoms to keep it neutral. Okay, so therefore there must be some positive charge within the atom to cancel out the negative charge of the electrons. This idea set the stage for future models of the atom, where scientists try to figure out how these positive and negative charges are arranged. Okay, now we will look at the earliest models of atom, that is the plum pudding model. This was the important step in our understanding of atomic structure. Okay, here is the diagram of plum pudding model, and notice how it shows us a sphere with small dots inside. We will use this image to help explain what scientists thought atoms looked like at that time. Okay, so now we'll talk about the first atomic model. Scientists were trying to figure out what atoms were made up and how their parts are arranged. Okay, so first model, atomic model, was proposed by or given by J.J. Thomson. Okay, so J.J. Thomson proposed this model in 1898. He had discovered the electron, a tiny negatively charged particle, and suggested that atom contain these electrons. Okay, so this model is called the plum pudding model because Thomson imagined the atom as a positively charged sphere with negatively charged electrons scattered throughout, like plums in the pudding. Okay, again diagram. Now let's go through the key features of Thomson's model. We will break down what makes this model unique and how it tried to explain the structure of the atom at that time. Pay attention to how the charges are arranged inside the atom. Okay, so Thomson suggested that positive charge in an atom is spread out evenly throughout the entire atom. Imagine the atom as a sphere where the positive charge fills the whole space, not just in one spot. Okay, this was a big shift from earlier ideas which didn't explain where the positive charge was. Next, he proposed that negatively charged electrons are embedded within this positive sphere. Think of the electrons as tiny particles stuck inside the positively charged pudding. This arrangement was meant to explain why atoms are electrically neutral overall. Okay, so finally the model gets its name from the way the electrons are scattered like seeds in a watermelon or plums in a pudding. Okay, so this analogy helps people visualize the structure. To sum up, the plum pudding model was an important step in understanding atomic structure. So let's examine the limitation of Thomson's atomic model. This model, sometimes called the plum pudding model, suggested that electrons were spread throughout the positively charged sphere like raisins in a pudding. Okay, so later studies proved Thomson model to be incorrect. Experiments, especially Rutherford's gold foil experiment, showed a result that couldn't be explained by this model. This was a turning point in our understanding of atomic structure. Okay, so the real distribution of electrons and positive charges was very different from what Thomson's proposed. Okay, so instead of being mixed together, electrons are found in specific regions around a small dense positively charged nucleus. Okay, so Thomson model was eventually replaced by more accurate atomic models. For example, Rutherford model introduced the idea of a central nucleus, and later Bohr model explained electron orbits. Each new model brought us closer to true structure of the atom. Okay, so even though Thomson's model was incorrect, it laid the foundation for the future atomic theories. It encouraged scientists to keep questioning and experimenting, which is a key part of how science progresses. Okay, let's start by looking at electromagnetic radiation from condensed matter. Okay, so condensed matter refers to solids and liquids where particles are packed closely together. Okay, so notice that solids and liquids emit radiation with a continuous distribution of wavelengths. This means they don't just emit a few specific colors or lines, but rather a smooth spread of all possible wavelengths. This is different from the sharp lines we see in the spectra of gases at low pressure. Okay, so dense gases can also show similar continuous spectra. When gases are at high pressure, their atoms are very close enough to interact, so their emission resembles that of solids and liquids. Okay, in which the molecules or atoms are closely packed. Okay, take a look at the image here. See how the spectrum is a smooth and continuous band of different wavelengths. Okay, different colors, different wavelengths, not just a few lines. This is called a continuous spectrum, and its key feature of dense matter. Okay, so the intensity of this radiation isn't the same at all wavelengths. Some wavelengths are emitted more strongly than others, creating a curve when we plot intensity versus wavelength. Okay, for example, a hot object like an bulb emits more in the visible range, while cooler object emit more in the infrared region. Okay, so the relative cooler object emit the infrared radiations, and very hot object, you can see when we heat up the iron, it becomes red, then reddish yellow, then yellow. Okay, its color changing, so it is emitting the visible emitting the radiations in the visible range. Okay, it start emitting the radiation in the visible range. Otherwise, if it is relatively cooler, we are heating up but not that much, it is emitting the radiation in the infrared region. Okay, so this variation help us determine the temperature and properties of material. So why does this radiation occur? It is due to the oscillation of atoms and molecules within the material. These particles are constantly vibrating and moving, and as they do, they emit electromagnetic waves. But what causes these oscillations? So it's the interaction between the neighboring particles in solids and liquids. Atom and molecules are packed so closely that they are always bumping into each other, exchanging energy. These constant interactions keep the particles vibrating, which leads to continuous emission of radiation. To sum up, in condensed matter like solids, liquid and dense gases, particles are closely packed and interact constantly. This leads to continuous oscillation and as a result the emission of continuous spectrum of radiations. Remember, it's the close packing and constant interaction that make the spectrum continuous, unlike the discrete lines we see in the low pressure gases. Okay, so let's look at how rarefied gases, okay, meaning gases at very low pressure, in which particles, molecules or atoms are very far from each other. Okay, their interactions are minimal. Okay, so meaning gases at low pressure emit electromagnetic radiation. This is a key idea in understanding atomic structure and how atoms interact with light. We will explore that what happens when these gases are energized. Now notice that the rarefied gases emit light at only certain specific wavelengths. This means they don't give off a continuous rainbow of colors, but instead produce light at distinct points in the spectrum. This is different from what we see with something like a regular light bulb, which emits a broad range of colors. Okay, so let's see how these gases can be made to emit light. We can excite the atom in these gases by heating them, such as placing them in a flame or by passing an electric current through them. Both methods give the atom extra energy, causing them to emit light as they return to lower energy states. Okay, so some everyday examples of this phenomena include neon signs which glow in bright light and mercury vapor lamps, often used in street lighting. In both cases, the color of the light comes from the specific wavelength emitted by the gas inside the tube. So if we look at the spectrum produced by these gases, we see distinct bright lines instead of continuous spectrum of colors. Okay, this image shows what that looks like. Each line represents light of a specific wavelength. Okay, so focus on how these lines are sharp and separated, not blended together. So each of these spectral lines corresponds to a specific electronic transition bit within the atom. This means that when an electron jumps from a higher energy state to lower one, it releases energy as a light at a particular wavelength. The position of each line tells us about the energy difference between those levels. Okay, so this pattern of separate distinct lines is called line spectrum or discrete spectrum. It's a key fingerprint for each element, helping scientists identify what elements are present in a sample. Okay, remember, unlike solids or gases, solids, liquids, or gases at low pressure always show this kind of spectrum. Okay, so except solid, liquids, or gases at high pressure, that is condensed or dense gases. Okay, except these type of materials, gases at low pressure, or we can say rarefied gases, always show this kind of spectrum, line spectrum. Now let's start by looking how electromagnetic radiation is produced by different type of matter. Okay, the title here is sets the stage. We are comparing condensed matter like solid and liquids with rarefied gases, which are gases at low pressure. Okay, so in rarefied gases, atoms are far apart from each other. Okay, because the atoms are so far apart, they don't really influence each other. Each atom acts on its own, almost as if it's the only one there. Okay, this independence is important because it means the behavior of one atom doesn't affect the others, which is different from what happens in solids or liquids. Let's see what this means for the light we observe. Since the emission comes from the individual atoms, not from group of atoms working together, the spectrum we see made up of distinct lines. Each line corresponds to a specific energy change within an atom, which is why we call it discrete or line spectrum. So let's summarize what we have learned so far. Okay, we are going to compare what happens in condensed matter and in rarefied gases. Notice how the difference in atomic spacing and interaction lead to very different type of spectra. Okay, so in condensed matter like solids or dense gases or liquids, the atoms are packed closely together. Their interaction causes the energy levels to blend, so the emitted light covers a continuous range of wavelength. This is why we see a continuous spectrum like the rainbow from a light bulb. In contrast, rarefied gases produce a discrete spectrum. Here only certain wavelengths are emitted, which shows up as sharp lines. This happens because the atoms are isolated, so only specific energy transitions are possible. For example, the bright lines you see in a neon sign are due to this effect. So the main difference between these two cases comes down to how close the atoms are and how much they interact. Okay, so in condensed matter, strong interaction lead to continuous spectrum, while in rarefied gases, weak or no interaction gives us discrete spectrum. Okay. Now we are exploring how the discovery of atomic spectra helps scientists understand the structure of atoms. Atomic spectra are the unique patterns of light that elements emit or absorb. These patterns gave us important clues about what atoms are like inside. So let's look at one atomic spectra were discovered in the early 19th century. Scientists started to notice something interesting when they studied the light given off by different elements. This was a key moment in physics and chemistry. So they found that each element produces its own unique spectrum of radiation. That means, for example, hydrogen gives off a different set of colors than sodium or helium. This uniqueness is like a fingerprint for each element. Okay, so the pattern of lines in the spectrum for each element always stay the same. Okay, for a particular element. So no matter where or when you look at hydrogen, its spectrum will have the same lines in the same places. This consistency was a big clue that something fundamental was happening inside the atoms. For example, hydrogen always produces spectral lines with fixed positions relative to each other. If you look at hydrogen spectrum, you will see the same set of lines like a barcode. This repeatability suggested that process creating these lines was tied to structure of atom itself. Let's talk about why this discovery was so important. The fact that each element has a unique and consistent spectrum made scientists wonder what was causing these patterns. It pointed to a deeper connection between the light atoms emit and their internal structure. This led to the idea that there is a direct link between the spectrum of radiation an atom emits and what's happening inside the atom. In other words, the way atoms are built determines the kind of light they give off. Specifically, it suggested that internal structure of atoms, how their parts are arranged and how they behave controls the spectrum we see. This was a major step towards understanding atomic models like Bohr model where electrons move between the energy levels. Okay, to sum up, the discovery of atomic spectra gave scientists a powerful tool to investigate the atomic structure. So let's begin with Balmer's contribution in 1885. This was a turning point in atomic physics as it provided the first real clue that atoms have an internal structure that affects the light they emit. Okay, so John Jacob Balmer, a Swiss mathematician, okay, developed an empirical formula to describe the wavelengths of visible light emitted by hydrogen. Empirical means it was based on observed data, not theory. This was important because it gave scientists a mathematical way to predict the lines they saw in hydrogen spectrum. Okay, so Balmer formula actually calculated the exact wavelengths of hydrogen spectral lines. This suggested a deep connection between the structure of atoms and radiation it emits. In other words, the light we see from hydrogen isn't random, it's tied directly to what's happening inside the atom. This was a major step forward in atomic spectroscopy, which is the study of how atoms absorb and emit light. Okay, Balmer's work showed that there was a pattern to these emissions, hinting that atoms have specific energy levels. This idea would later be crucial for the development of quantum theory. So let's focus on hydrogen. Hydrogen is the simplest atom with just one proton and one electron. Because of its simplicity, it's the perfect starting point for understanding atomic spectra and the underlying physics. Hydrogen simplicity makes it easier to study and model. With only one electron, the interactions are less complicated than in larger atoms. Okay, so we will study hydrogen spectrum in detail in this chapter. By analyzing the lines it emits, we will uncover the rules that govern all atoms. This detailed look at hydrogen will help us build a foundation for understanding more complex elements later. Hydrogen serves as a fundamental example for understanding atomic spectra. This pattern we see in hydrogen spectra are starting points for all atomic physics. Okay, now we are focusing on Rutherford's alpha particle scattering experiment, a key moment in the history of atomic physics. So let's start with Ernst Rutherford. He was a former student of J.J. Thomson who discovered the electron. Rutherford studied alpha particles, which are the nuclei of helium atoms, meaning they have two protons and two neutrons and carry a positive charge. Focus on that alpha particles are much heavier than electrons and can be detected as they pass through materials. In 1906, Rutherford came up with an experiment to learn about the atomic structure. He wanted to see how alpha particles scattered or change direction when they pass through thin sheets of material. This idea was important because it could reveal what atoms are really like inside, whether they are mostly empty space or filled with mass. The actual experiment was carried out around 1911 by two of Rutherford's colleagues, Hans Geiger and Ernst Marsden. Okay, so Geiger is known for inventing the Geiger counter, which detects radiation. Marsden was a young scientist at that time. So it's interesting to note that Marsden was only 20 years old and hadn't even finished his bachelor degree when he helped with this groundbreaking experiment. This shows that important scientific discoveries can involve people at any stage of their careers. The Geiger-Marsden experiment, which is also called the gold foil experiment. The surprising results from this experiment led Ernest Rutherford to propose the planetary or nuclear model of atom. Notice how this was a big shift from the earlier plum pudding model, which was imagined positive charges spread out evenly. Here, the experiment showed that most alpha particles pass straight through the foil, but some bounced back, suggesting a dense center. According to Rutherford's nuclear model, almost all the atoms' positive charge and mass are packed into a tiny central region called the nucleus. The nucleus is extremely small compared to the overall size of the atom, but it contains nearly all the mass. Rutherford also proposed that electrons move around the nucleus, similar to how planets orbit the sun. This is why it's called planetary model. This idea helped explain why atoms are stable and why they don't just collapse. Okay, so let's look at Rutherford alpha particle scattering experiment. So Rutherford nuclear model was a huge step forward. It showed that atoms have a tiny dense nucleus at the center with electrons moving around it. This idea helped us move beyond the old plum pudding model where atoms were thought to be a mix of positive and negative charges spread out evenly. Okay, so there are some limitations of Rutherford model also. So it had some big limitations. Let's look at what it couldn't explain about atoms. So Rutherford model couldn't explain why atoms only emit light at certain specific wavelengths. In other words, when we look at the light given off by atoms, we see sharp lines, not a continuous rainbow. This was a big clue that something was missing in the model. Another problem was that model failed to explain atomic spectra. Atomic spectra are the unique patterns of light each element gives off. These patterns are like fingerprints for elements, and Rutherford model couldn't account for why they exist. Okay, so the hydrogen atom, the simplest atom with just one proton and electron. Even hydrogen produces a complicated spectrum with specific lines, not just a single color. This shows that even the simplest atoms behave in ways the classical model couldn't predict. So in the classical model, people thought electrons orbited the nucleus like planets orbit the sun. This seems logical at first, but it leads to problems. For example, according to classical physics, the electron should spiral into the nucleus, which doesn't happen. This planetary model faced serious issues that couldn't be ignored. It couldn't explain why atoms are stable or why they emit light in specific patterns. Scientists realized they needed a new way to think about the atomic structure. So the classical model just wasn't enough to explain how atoms really work. This led to the development of new models like Bohr model, which we will explore next. Okay, now we will discuss the alpha particle scattering and Rutherford's nuclear model. Okay, so let's start with Ernest Rutherford, a former student of Thomson, J.J. Thomson, who proposed the plum pudding model of atom. Rutherford suggested a new experiment firing alpha particles. These are helium nuclei with 2 protons and 2 neutrons at thin metal foils to see how they scatter. This was a clever way to probe the inside of atoms, which were still mysterious at that time. Building on Rutherford's idea in 1911, two scientists named Hans Geiger and Ernest Marsden carried out these experiments. It's important to note that this was a team effort and their careful observations were crucial. In one of their key experiments, they used a radioactive source, okay, specifically bismuth 214. 214 is its atomic weight, okay, and 83 is its atomic number, okay, which emits alpha particles. Bismuth they used radioactive bismuth they used for emission of alpha particles. Okay, so figure 12.1, the setup involved directing these alpha particles at a thin gold foil and detecting how they scatter. The entire apparatus was placed in a vacuum chamber to prevent air molecules from interfering. This experiment provided the evidence that led to the nuclear model of the atom, which we will discuss in detail next. Okay, so you can see in figure 12.1, that is Geiger-Marsden scattering experiment. The entire apparatus is in the vacuum chamber. Okay, and source of alpha particle is used here is bismuth, radioactive bismuth. Okay, that is bismuth 83214, and that bismuth is producing alpha particles, and that alpha particles are direct towards the gold foil, and screen is placed. Okay, and then readings are noted. We will discuss the observation of this experiment in the further slides. Now we are going to discuss Rutherford alpha particle scattering experiment, which was a key experiment in understanding the structure of the atom. Okay, so take a look at figure 12.2, which shows a schematic diagram of this experiment. So this is figure 12.2. Here is the actual schematic diagram of Geiger-Marsden experiment, also known as gold foil experiment. Point out the source of alpha particles and thin gold foil in the center. Okay, and the detector that moves around to catch the scattered particles. This setup allowed Rutherford and his team to observe how alpha particles interact with atoms in gold foil. Okay, so zinc sulfide screen, it is used. So when alpha particle, after scattering through the gold foil, fall on this screen, it produces a small, it produces luminous dots. Okay, and that's how scattered alpha particle are detected. Okay, also detector microscope is used. Okay, and beam of alpha particle is directed towards the gold foil, and their scattering angles, that how many alpha particles are scattered through which angle, is noted. Okay, all the observations and readings are noted. This is the schematic diagram. Source of alpha particles is lead bricks. Lead bricks are there. Why lead bricks are there? To produce a beam of alpha particles, not just the alpha particles scattered in all directions. We just need a beam of alpha particles that is incidenting on the gold foil. Okay, so the alpha particle used in this experiment came from a radioactive isotope of bismuth, written as bismuth 214. Okay, so these particles were formed into a narrow beam using lead bricks, which acted as collimators. Collimators help to focus the particles into a straight, narrow path, make the experiment more precise. Okay, so this narrow beam of alpha particles, each with an energy of 5.5 mega electron volt, okay, was aimed at a very thin sheet of gold foil. The foil was only 2.1 times 10 to the power minus 7 meter thick. Okay, which is extremely thin, about 1,000 times thinner than a human hair. Okay, this thinness allowed most alpha particle to pass through, but some would interact with the atoms in the foil. Finally, a movable detector was placed around the foil to observe where the alpha particles went after hitting the gold. By moving the detector to different angles, the scientist could measure how many particles were scattered in each direction. This data was crucial for understanding structure of atom. Here you can see a diagram of the experiment setup again. The detector in this experiment was made of zinc sulfide screen and a microscope. Zinc sulfide is important because it lights up when hit by alpha particles, making it possible to see where the particles go. The microscope allowed scientists to observe these tiny flashes of light closely. When an alpha particle struck the zinc sulfide screen, it produces a brief flash of light. Okay, each flash represents a single alpha particle. Okay, these brief flashes of light are called scintillations. Okay, each flash represented a single particle, alpha particle, hitting the screen. This allowed the scientists to count individual particles and see exactly what they landed. Okay, so scientists used a microscope to view these flashes of light. This was necessary because the flashes were very faint and short lived. By carefully observing through the microscope, they could accurately record each event. By moving the detector to different angles around the gold foil, scientists could study how the alpha particles scattered. This means they could see if the particles went straight through, bounced off at small angles, or even bounced almost straight back. The angle of scattering gave clues about what was inside the atom. Okay, finally, the number of scattered particles was recorded at each angle to create a scattering pattern. This pattern helped scientists understand the distribution of mass and charge inside the atom. This experiment showed that most alpha particles passed straight through, but a few were deflected at large angles, leading to the discovery of atomic nucleus. Okay, so now we are looking at some key experimental observations about atoms, specifically from experiment involving alpha particles and thin metal foils. So let's start with the main findings. So many of the alpha particles pass through the foil. It means that they do not suffer any collisions. Most alpha particles pass through the little deflection. Okay, so means they are deflected by small angles. Even more striking, a very tiny number of uh, alpha particles were deflected through angles greater than 90 degree. Okay, this is called backscattering. Okay, imagine throwing a ball at a wall and having it bounce back at you. That's what happened to few these particles. Okay, so only about 0.14% of incident alpha particles scattered by more than 1 degree. Okay, and very few alpha particle deflected through angles that are greater than 90 degree. Okay, and very few particles backscattered. Okay, so put numbers on it. 1 in every 8,000 alpha particle was scattered through an angle greater than 90 degrees. This is quantitative result. So very few means 1 in every 8,000 alpha particles that is deflected through greater than 90 degrees. Meaning we can use it to estimate the size and charge of the atomic nucleus. The fact that it's so rare tells us nucleus is extremely small compared to the whole atom. Okay, so quantitatively 1 in the 8,000 particles scattered through greater than 90 degree angle. Now let's look at the experimental observations. So we have statement about the data collected in these experiments. Scientists measure how many alpha particles were scattered at different angles over certain period of time. This information was then plotted on a graph which we will look at the next. Okay, so let's examine the actual graph from the experiment. The dots represent the real data points collected by Giger and Marsden. Okay, and while the solid curve shows the prediction made by Rutherford's nuclear model. Notice how closely the experimental result matched the theoretical prediction. This strong agreement was key evidence supporting the Rutherford's idea that atoms have a small dense nucleus. Okay, so you can see in the plot that dots are representing so that data points. Okay, so in the x-axis scattering angle theta is given, and along y-axis it is number of scattered particles detected. Okay, so you can see for large angles number of scattered particles are very small. Okay, for large angles greater than 90 degree, so number of scattered particles are very small. For small angles, okay, the alpha particles that are scattered through very small angles less than 40 degree, okay, or nearly 20 degree, that are very large in number. Okay, So to summarize, the graph clearly shows that experimental data points line up well with the theoretical curve. This tells us that Rutherford nuclear model accurately describes how alpha particle scattered, okay, confirming the existence of central nucleus in the atom. So let's see the experimental observations again. So the theoretical curve shows here is based on a specific model of the atom. This model makes certain assumptions about what atom is. Okay, like inside. Let's break down these assumptions one by one to see why they matter. So first, the model assumes that nucleus of the atom is very small compared to the overall size of the atom. This means most of the atom is actually empty. Second, the nucleus is not just small but also extremely dense. This means it contains almost all the mass of the atom packed into a tiny volume. For example, if you could compress this mass of a person into nucleus size space, it would weigh the same but be invisible to the naked eye. Finally, the nucleus carries a positive charge. This is important because it explains why a positively charged particle like alpha particle are repelled when they come close to the nucleus in the experiment. So let's look at what Rutherford observed. He noticed that some alpha particles, which are positively charged particles, were deflected backwards when they hit a thin gold foil. This was surprising because according to the old model, atoms were thought to be mostly empty space with evenly spread positive charge. The strong backward deflection suggested that there was a powerful repelling force inside the atom. To explain this, Rutherford proposed that almost all of the atom's mass and its positive charge must be concentrated in a tiny central region, which we now call the nucleus. This was a big change from the previous plum pudding model, where positive charge was spread out. The nucleus is extremely small compared to the overall size of the atom, but it contains nearly all the mass. Alpha particles, being positively charged, could get very close to this concentrated positive center, but they couldn't pass through it. Instead, they were strongly repelled and deflected at large angles. This explains why only a few alpha particles bounce back while most pass through the atom with little or no deflection. It's important to note that atomic electrons are much lighter than alpha particles. Because of this, electrons don't significantly affect the path of the alpha particles during the experiment. The main interaction is between the alpha particle and the massive positively charged nucleus. When Rutherford experimental result matched this explanation, it provided strong support for the nuclear model of the atom. This model replaced the earlier idea of diffuse positive charge and led to our modern understanding of atomic structure. So Rutherford work led to discovery of atomic nucleus. His experiment changed the way we think about atoms and laid the foundation for modern nuclear physics. So what were the model conclusions? So let's look at the main conclusions of Rutherford model. These are the key points that came out of this famous gold foil experiment. So first, Rutherford found that almost all of the atom's positive charge and most of its mass are concentrated in a tiny central region called the nucleus. The nucleus is extremely small as compared to whole atom, but it contains nearly all the mass. So let's talk about the size of the nucleus. Rutherford experiment suggested a nucleus is about 10 is power. So the size of the nucleus is about 10 is power minus 15 meter to 10 is power minus 14 meter. Okay, so an atom's total size according to kinetic theory measures approximately 10 is power minus 10 meters. Okay, so the nucleus is significantly smaller, with the atom being 10,000 to 1 lakh times larger than its nucleus. Okay, so atom is significantly larger, which is 10,000 times or to 1 lakh times larger than its nucleus. So electron move around the nucleus at distances that are 10,000 to 1 lakh times greater than the diameter of the nucleus. You can imagine the nucleus as a tiny dot in the center of a large stadium with the electrons moving far away from it. This helps us understanding why atoms are mostly empty spaced. Because the electrons are so far from the nucleus, the vast majority of an atom's volume is just empty. This explains why atoms can be compressed and why most of the mass is concentrated in the nucleus. So let's focus on the electrons. According to Rutherford, electrons revolve around the nucleus, similar to how planets orbit the sun. This planetary model helps scientists visualize atomic structures. Even though we now know electrons behave a bit differently due to quantum mechanics. So let's compare the sizes. The radius of the nucleus is about 10 raised to power minus 4 times the atomic radius. Okay, so this size ratio highlights just how small the nucleus is compared to the atom as a whole. So notice that the gold foil used in the experiment is extremely thin. This is important because it means the most alpha particles, which are the particles being fired at the foil, will only interact with one gold atom as they pass through. This makes the analysis much simpler since we can focus on single scattering events. Because the foil is so thin, we only need to calculate what happens during a single collision between an alpha particle and a gold nucleus. This allows us to ignore the possibility of multiple scattering, which would make the math and the interpretation much more complicated. Let's talk about the alpha particle themselves. Alpha particles are actually helium nuclei, which means they have a charge of plus 2 times the charge of an electron, that is plus 2e. Okay, their mass is about the same as helium atom, which is roughly 4 atomic units. Okay, the gold nuclei that the alpha particle are hitting have a charge of plus 79 times the charge of an electron, that is plus 79e. Okay, here Z stands for the atomic number, which is 79 for gold. This large charge, positive charge, creates a strong repulsive force when an alpha particle gets close. Finally, it's important to realize that gold nucleus is much heavier than the alpha particle, about 50 times heavier in fact. This means we can treat the gold nucleus as if it doesn't move during the collision, which makes our calculation much easier. So to understand how Rutherford figured this out, let's look at how alpha particles move when they approach a nucleus. Their path can be predicted using two fundamental laws of physics. We will see what these laws are and how they help us understand the experiment. The first law is Newton's second law of motion. This law tells us that the force acting on an object equals its mass times its acceleration, and F equal to ma. This is a basic rule that applies to all moving objects, including alpha particles. The second law is Coulomb's law, which describes the electrostatic force between the two charged objects. In this case, it's repulsion between the positively charged alpha particle and positively charged nucleus. Now let's look at the actual formula for the electrostatic force between the alpha particle and the nucleus. This force depends on the charges involved and distance between them. So the formula is F equal to 1 upon 4 pi epsilon naught 2e, that is the charge of alpha particle, and Ze, that is the charge of the gold nucleus, upon r square. Okay, so here r is the distance between the alpha particle and the nucleus. The force is directed along the line joining the alpha particle and the nucleus. So this is a central force. Okay, this means the direction of force changes as alpha particle moves, not just its strength. Finally, remember that as the alpha particle move towards and then away from the nucleus, both the size and direction of the force changes continuously. Okay, this explains why some alpha particles are only slightly deflected while others are scattered at large angles. So now we'll summarize today's lecture in some brief points. Atomic hypothesis of matter. By the 19th century, scientists had gathered strong evidence that matter is made up of tiny particles called atoms. In 1897, J.J. Thomson discovered the electron, which is negatively charged particle found inside atoms. Thomson's model of atom suggested the plum pudding model, where the electrons are the scattered through a sphere of positive charge like raisins in a pudding. This model tried to explain how negative charge electrons and positive charge could balance out to make a neutral atom. Scientists study atomic spectra. When they looked at light from dense materials, they saw continuous spectra, but rarefied gases produces line spectra, distinct lines of color. John Balmer uh, developed a formula to predict the wavelengths of hydrogen spectral line. In this formula, each variable represents a specific energy transition in the hydrogen atom, and the wavelengths are measured in meters. So we will see that empirical formula in the further lectures. Moving on, Rutherford, Giger and Marsden performed a famous experiment using alpha particles and thin gold foil. Alpha particles are positively charged and much heavier than the electrons. In this experiment, they shot these particles at the foil to see how they would scatter. The results were surprising. Most alpha particles passed straight through the foil, but a few were detected at large angles. Few were deflected at very large angles. Okay, this meant that the positive charge in the atoms must be concentrated in a tiny dense nucleus, not spread out as Thomson's thought. Rutherford nuclear model of atom proposed that atoms have a tiny dense positively charged nucleus at the center with electrons orbiting around it. This was a big change from earlier models, showing that most of the atom is actually empty spaced. Let's look at some problems with the nuclear model. According to classical physics, any charged particle moving in a circle like an electron orbiting the nucleus should give off energy as electromagnetic radiations. This means the electron would lose energy and spiral into the nucleus, causing the atom to collapse. But we know atoms are stable, so this prediction doesn't match reality. Okay, so nuclear model also couldn't explain why atoms only emit or absorb certain colors of light known as line spectra. If electrons could have any energy, we would see a continuous spectrum, but experiments show only specific lines. This told scientists that a new theory was needed to explain atomic stability and this unique spectra. Despite its problems, Rutherford model was supported by experimental data. When scientists fired alpha particles at thin gold foil, most passed through, but some bounced back at large angles. This matched Rutherford prediction and confirmed that atoms' positive charge is concentrated in a small nucleus. So while the model wasn't perfect, it was a crucial step forward in understanding atomic structure. Now let's see some practice questions based on today's lecture. Okay, so in 1897, scientists used experiments with electric discharge through gases to uncover the existence of electron. Okay, so who discovered the electron through these experiments? So what was the nickname given to Thomson's atomic model where electrons were embedded in a positive charge distributions? So Rutherford famous gold foil experiment, he found that only a tiny fraction of alpha particle were scattered at angle greater than 90 degree. Okay, so what fraction of these alpha particle were scattered at angles greater than 90 degree in Rutherford experiment? Okay, so according to Rutherford model, the nucleus is extremely small compared to the overall size of the atom. So what is the approximately what fraction of the atomic radius was the nuclear radius? And finally, let's look at the hydrogen spectra. Okay, so who developed the empirical formula in 1885 for predicting the wavelengths of hydrogen spectral lines? Okay, so these are some practice questions. So I hope you enjoyed the session. Thank you. This is all about today's lecture.